Good morning. We are back looking at Chapter 6, looking at gravity, and we have gone through the general gravitational formulas that Newton developed 350 years ago, something like that, and they still are very useful, so we continue to use these in doing all of these gravitational calculations. We had reached a point in the chapter where we wanted to look at orbits. We'd started talking about gravitation as a force that enables us to put things in orbit. So we can launch something, give it a particular speed, and if the speed sort of matches the distance or the radius of the circular motion around the Earth or another planet or the Sun, then we can come up with a stable orbit. Now the orbits don't have to be circular, they could be elliptical, but we want to look at the simplest types of orbits, and those are the circular orbits. The ellipticals are involve a little more complexity. So the first example we said that we wanted to look at was a geosynchronous satellite, and the idea with a geosynchronous satellite is that, well, this one, so let me look at the diagram I had drawn here. So let's say this is the Earth. I'm going to identify where the center of the Earth is located because we can treat the gravitational forces as if they're coming entirely from the center. They're not. They're coming from all parts of the planet. But in our formulas, we want to be able to measure, when we bring in gravitational forces right here. So here's our gravitational force formula. The distance in that denominator needs to be center to center between the satellite and the Earth. Now for the satellite, that's not a big deal. The satellite's not a very big object. But the Earth is. And so we have to make sure we're coming from the center of the Earth, measuring out to center of the satellite. For a circular orbit, we're going to make use of circular motion. So we're bringing in our circular motion equation, v squared over r. That's an r, it really is. This is also an r here. And we said that we could, we originally wrote this kinematic equation for circular motion as v squared over r, but since then we've adjusted it. So now we are also using 4 pi squared r over period squared. We said this one becomes useful because often we're working in terms of not velocity, but in terms of period of the orbit. How much time does it take to complete one orbit? In this case, it's one circular orbit that we'll be looking at. So putting these two formulas together, well, let's do this first. So from the laws of motion, we can say that the gravitational force will result in an acceleration. And that acceleration is given by F over m, and that's given by big G, big M over the distance squared. And so as you can see, this expression, that's the gravitational field at a certain location, at a certain distance from where the center of the Earth is located. So it works the same way as near the surface of the Earth. Near the surface of the Earth, we said the acceleration equals the gravitational field if we neglect air resistance. And now we're saying the same thing happens in these orbits. The gravitational field out here where the orbit is located is going to be reduced from what it was at the surface of the Earth, but we can come up with that gravitational field or that acceleration by putting in a different value of r. The value of r will take care of that for us. So we're going to take this expression, the acceleration is gm over r squared, and set it equal to our kinematic expression for acceleration. And so this is what it looks like. V squared over r, here's a kinematic expression in terms of v. Here is our kinematic expression in terms of period. And we're going to set that equal to the gravitational field. big G, big M over distance squared. Now we'll get two equations here. One of those will be for velocity, so the speed at which a satellite will be traveling in a circular orbit, a stable circular orbit, would need to be big G, big M over the distance. And that's the velocity squared, so if it's just velocity, we got to take a square root on that right side. The formula just below that comes from using this expression and then solving for period. So when I do that, the period squared is equal to 4 pi squared, r to the third, divided by big G, divided by big M. So those are our two formulas. This is going to relate V and R. This is going to relate period and R. So, and these are for circular orbits. So let's get back to geosynchronous now. So geosynchronous, here's the Earth. Here's the center of the Earth. Here is the velocity of our satellite. And so here's a satellite in orbit. We need, well, let's keep track of a couple of R's. Here's the radius of the Earth. I'm going to call that big R. Now that's probably not going to play into this. It doesn't really, nothing here depends on what big R is necessarily. It really depends on the distance from the center out to the satellite. Now we had looked at rotational periods of the Earth earlier and said that they're really not 24 hours. They are 23 hours, 56 minutes and 4 seconds roughly. So that gave us 86,164 seconds. Now I'm going to take that formula that we derived on that previous page, solve for R cubed. And the reason for that is we know the period. The period's got to match the period of rotation of the Earth. And so we're going to put in big G, and we're going to put in the mass of the Earth. Here's the mass of the Earth here. And then I guess we plug all the numbers in. So gravitational force constant, mass of the Earth, we got all these numbers. So here is the calculation. So I put all the numbers in with their units because we want to check and make sure units are going to cancel out. So what we have here, we've got a lot of units. We got kilograms squared here. There's a kilogram that cancels here. Newtons include kilogram, meter, divided by 2 factors of seconds. And so the other kilogram will cancel out. I got 3 factors of meters here now, divided by seconds. The second squared will divide out right there. So we're really left with 3 units of meters. And then we have a cube root. So 3 factors of meters are all that's left. And we take the cube root, and that reduces back down to 1 unit of meters, which are lengths. And that's what we're solving for. We're solving for a length or a distance. We're solving for little r. Now putting everything in, I ended up with 42 million meters. And then I did a conversion into kilometers. So don't let that throw you off. I originally did the calculation in meters, looked at the numbers, and then divided through by 1,000. So this is what the r value would be. Now 42,000 kilometers, that's a good distance. The radius of the Earth is, just for comparison, so we are going to use the big R, for comparison, the radius of the Earth, 6,370 kilometers. But these satellites, if they're going to remain geosynchronous, need to be placed in an orbit at 42,000 kilometers, 42,170. So that's like, 6 or 7 Earth radiuses from the center of the Earth. So they're going to be way, so this is not to scale. So it turns out if the Earth is this size, the geosynchronous orbits would need to be out here somewhere, a great big circle going around the Earth. And then the other issue that comes up is, well, if they're geosynchronous, where can we in general, I guess, place these orbits? Do the orbits have to match up with latitude? does the plane of the satellite orbit have to match the rotation of the, does the orbits have to be over the equator, I guess. So here's the restrictions. If you think about this, the plane of the orbit has to pass through the center of the Earth. Now that doesn't say that it has to be along the equator. It could be tipped. So you could have an orbit that is tipped so that the orbit relative to the equator. You could even have what's called a polar orbit. You could have something orbiting the Earth in a polar fashion, so the Earth could be rotating underneath, and there would be this polar orbit that would be going over the poles as the Earth rotated within that. And then for a geosynchronous orbit, every time one orbit completes, the Earth would have gone around once. So you should be traveling over the same regions on each orbit. Those two would be synchronized. There would be one path that the satellite, on the surface of the Earth, a circular path that the satellite would be following during that time. Okay, I think that's it. So we did the circular orbit stuff. We're using those. But this one in particular is geosynchronous. That's the thing to remember here. Yeah, I think that's everything. So let's ask one more question, I guess. What would happen? Why wouldn't a closer orbit work? And if we went to a closer orbit, we would have to be traveling faster. Okay, an orbit that's closer in, an orbit. Where's the best place to see that? If we went with a smaller value of r, the period would reduce. Okay, and so and it would be traveling faster. I guess we got to go back. So these formulas, once we plug some of this stuff in, we got to get back to the original formulas. So let's say this: if we went to a smaller orbit, a lower r value for the orbit, then the v would have to go up. So in a lower orbit, v is going to need to be a larger number. And then what will also happen in the lower orbit is the period will be reduced. So the satellite would be traveling faster, it doesn't have as far to travel, and so the period would be reduced. It would no longer synchronize with the rotation of the Earth. For orbits beyond geosynchronous, those orbits, the satellite would need to be traveling slower, more slowly out there, and the period would be increased. It would be traveling more slowly. The orbit itself would be larger if the radius of the orbit got bigger, and that's going to take more time. The satellite's not going to keep up with the rotation. Now here's an example, just to compare. This is a circular orbit also, let's say, but this is a low orbit. You know, some of the lowest orbits are at a couple hundred kilometers. So you can actually put in something in orbit at kind of this close. And in that case, if it's 200 kilometers above the surface of the Earth, we need to take the radius of the Earth, add on the 200 kilometers. That will give us 65, 70 kilometers for the radius of the orbit, right? The radius of the orbit is going to be measured from the center of the Earth out to the surface and then out and beyond. So we would, if we're given this number, 200 kilometers above the surface, then we want to add those together, 6370, 200, to get the 6570. For this, we can plug in to our velocity formula that we derived, and it says that the lowest orbits that are possible, due to the presence of Earth's atmosphere, we can't get much lower than this and have a stable orbit. Those orbits would be the very fastest that are possible, and those orbits you would need to be traveling 77, 91 meters per second. So that's much faster. When you put the time in for these, These take 5,300 seconds. It's about an hour and a half. So if you've watched these space shows, you'll know that when they're talking about orbiting around the Earth in low orbit, it's about 90 minutes. Okay, just for comparison, the geosynchronous, we're traveling at 3,100 meters per second, and these are traveling at 7,800, so more than twice as fast in those low orbits. And the periods are changing from roughly 24 hours down to just 1.5. The orbits are much smaller. The circumference of that circle is much smaller at that low orbit, and we're traveling faster. Both effects play into this. All right. So it says that you are trying to catch a satellite. You find yourself in a circular orbit of the same radius, but you're behind the satellite. How do you catch up? So let's say, here you are in the space shuttle. You're trying to catch a satellite that's out ahead of you. You've placed the shuttle has been placed in an orbit that matches the satellite. You're in the same circular orbit. Problem is, you can't catch the satellite because you're traveling at the very same speed. So somehow you've got to get out ahead of the satellite. Now, boosting yourself into a higher circular orbit means you'll actually be traveling more slowly. So the way to catch up with the satellite is actually bring yourself into a lower circular orbit just below where the satellite's traveling. Bringing it down to a lower orbit will allow you to pass the satellite. So you can pass the satellite from below, it being in that lower orbit, and then once your orbit, your speed is higher, once that higher speed and shorter distance, you're kind of getting the inside track here. That higher speed and shorter distance eventually will allow you to catch up and pass the satellite from below, and then you can rise back up to your original circular orbit. So we're going to stick with circular orbits here, because if the satellite's in a circular orbit, if you put yourself in an elliptical orbit, that's just going to have you traveling away from the satellite in any case. Okay, so this is the maneuver that we're going to try, making use of the faster orbiting speeds and shorter orbiting distances in order to catch up and pass that satellite. So here we are with, I think we've looked at this before, let's see. So here we are in an elevator. Here's a person in an elevator, and this is really, I don't want to call it weight, I guess. Let's say that it's normal force, or it's tension. If it's the force holding this up, then there's a tension on that bag of whatever's inside there. So there's a tension holding that up, there's a gravitational force that's down. If the elevator is traveling at a constant speed, then that would tell us that the tension needs to equal mg. Now they've got the string or the rope holding this bag set up to a tension scale, and so we're actually able to measure how many newtons of force are there. And it looks like here we're at 20 newtons. So the gravitational force is 20 newtons, the tension in the string is 20 newtons, and we have a scale that we can just read, and it's telling us the very same thing, 20 newtons. What happens when we accelerate upwards? Well, what we found was that now the force, let's see, for the weight, that force is a tension. For the person, that upward force is a normal force. So I would prefer they write it that way. So there's a normal force pushing up on the person. I should have gotten in and edited. I missed this when I was going through the slide. So let's get a normal force in this direction, and we'll say that the normal force pushing up on the person equals the gravitational force. Now what we can do is let's accelerate. Now they're going to accelerate at a pretty good acceleration. This is an extreme elevator. This elevator could almost be an amusement park ride because they're going to accelerate at 1/2 g, 4.9 meters per second squared. So that's a pretty large acceleration. And as a result of the additional 1/2 g of acceleration, the gravitational force is increased by that same proportion. So it increases by 1/2 g. So you can see that the acceleration is leading to larger tensions in the support cable. This has gone from 20 newtons to 30 newtons. And the person now, if they've got a set of scales that they're standing on, those scales will read 50% higher. Okay, and the person has to be strong enough to support that additional force. Now, what happens if the acceleration, this is even more extreme, they cut the cables. Oh look, the cable's cut. Cable's cut, and now everything is dropping at the gravitational acceleration. And so we've got an acceleration of g downwards, and now everything's in free fall. So there is no tension in the cable. The person is not necessarily standing on the floor anymore. If there's a bathroom scale, the bathroom scale could separate from the floor as the elevator and the scale both free fall. The person's going to weigh nothing if we're thinking in terms of normal force. So the normal force supporting the person would drop down to be 0. Okay. So in all these cases, just to be clear, the gravitational force here is mg, the gravitational force here is mg, the gravitational force here is mg, but the force needed to support the person varies depending on what the accelerations are. Okay, now what they're doing is they're coming back and saying more properly this effect should be called apparent weightlessness. So this is why I have those issues with the word weight, is now we're into the realm of calling it apparent weight. And so just referring to the normal force or referring to the tension in the cable, I think simplifies things. So we want to be clear, if we've got something in orbit, the gravitational force is still there. In fact, the gravitational force is what's maintaining the orbit. That satellite is not going to go in a circular path without some kind of a force. If there's no force acting on the satellite, the satellite's going to go in a straight line. So there's definitely gravitational force. Same thing with the occupants inside the space station or inside the spacecraft. They too are in a circular orbit along with the spacecraft. So it's kind of like being in this elevator, right? The elevator's in free fall, the people inside are in free fall. The tension here has dropped to 0. Everything inside the elevator is just kind of floating around within the elevator itself, even though someone outside could see that they are in motion. The elevator is dropping, the contents of the elevator are dropping. Same thing with these spacecraft. So the spacecraft are doing the same thing. Now, here are the elliptical orbits, and as I mentioned, these are a little bit complicated. We're going to take one look at this diagram. I think there's one homework problem. Just to get, so you guys are familiar with elliptical orbits, but we're going to keep this pretty simple. We're not going to ask any involved questions about elliptical orbits. So just for reference here, Johannes Kepler published these findings in between 1609 and 1619. Now that's like 70 years before Newton came up with formulas for gravitation. So this was, 60, 70 years before Newton developed his ideas mathematically. Kepler did everything geometrically. So what Kepler found from really spending a lot of time very carefully going over all of this planetary data not that he had collected, but that had been collected by Tycho Brahe, a Danish astronomer, had painstakingly collected very detailed information on planetary motion. In particular, Mars had been followed very closely. Kepler was able to go in and look at this data and analyze it in terms of a heliocentric model with the sun at the center of the solar system and the planets in orbit. And one of Kepler's big contributions was Kepler realized these orbits aren't circular, they're elliptical. And once Kepler had allowed for the possibility of elliptical orbits, found that the path of the planets followed certain principles that he came up with. So if you think of Copernicus, Nicholas Copernicus, as a key individual in promoting the heliocentric model, where the sun was at the center of the solar system with planets orbiting, Copernicus stuck with circular orbits, and the circular orbits did not match the data. People could point out that assuming the sun at the center and the planets in circular orbits, there were variations. Careful measurements would show planets weren't following those circular paths. Kepler found out that if you allowed for ellipses, then it worked, and it worked perfectly. And so here's the idea. So we have an ellipse. Now, I don't know if how much time you spend in your math classes looking at ellipses, here is an ellipse. And so what we have is, here's the center of an ellipse, kind of like a flattened circle. The longer axis, they're going to divide up into distances of s. Those are called the major axis is from Q to R, and a semi-major axis is the distance s. So s to the center out to this point, s to the center out to this point. And then there's a shorter axis, and we're going to call that distance b. The key feature here to keep in mind is that in this elliptical orbit model, the large object with lots of mass, in this case it's the sun, is not at the center of the ellipse. It's not at the center. It's at what's called one of the focuses. So there are points within the ellipse called focuses. This is focus 1 and focus 2, where if you measure to any point on the ellipse and you measure distance from focus 1 plus distance to focus 2, they add up to be the same number. So people had been studying geometry for hundreds, really thousands of years, right, before this time. So people had been studying geometry for thousands of years, and along the way they had developed a pretty good understanding of properties of ellipses. And so this was something that people had developed, and for Kepler, this was an important way of thinking about what the geometric possibilities were, and it turns out it works. Now, present day, now that we have Newton's formulas for gravity, we can start from Newton's laws of gravity and derive an elliptical orbit in terms of the laws of gravity and the laws of motion. So, that would be the approach we would take today, but pre-Newtonian gravitation formulas and Newtonian laws of motion, Kepler was just working with geometry. And so anyway, again, the key feature here is that the sun, the large mass object, is at one of the focuses, and that means it's off away from the center. And what that does is it says that these elliptical orbits, they have a place where they pass the central object very closely a perihelion, and they have a location where they are the farthest away. So there's an apogee and a perigee, I think is what they're called. I think, I better check on this. This is perigee is the closest approach, apogee is the farthest approach within the orbit. So you can see that the orbiting object is not maintaining a fixed distance. It's not circular with the sun at the center. The planets are in these elliptical orbits. Now this is exaggerated. Most of the planets are in orbits that don't have very much elliptical nature to them. They're roughly circular. But you know, there's a significant, there's an easily measurable effect due to this elliptical nature of the orbits. So going back, these are the rules or Kepler's laws that he found for planetary motion. He found out that the orbit of each planet is an ellipse with the sun at one of the focuses. So this is in general for orbits around any object. If we put a satellite in orbit around the Earth, same thing would apply with a satellite orbiting the Earth as the central object. And then, what Kepler found, this is kind of interesting, is that if we measure equal time periods, let's say we follow this planet for a couple of months, and we find out it has traveled this far in its orbit. Well, if later on we follow the same planet for a couple of months when it's farther away from the sun and measure how far it's traveled, it's different. When the satellites are or when the planets are closer to the sun, they're traveling faster. So in these nearer regions of the orbit, the planet travels faster, and then as it moves away, it travels more slowly. So as it's approaching the sun, part of the sun's force is speeding it up. And then as it's traveling farther away from the sun, the lower part of the orbit shown here, part of the gravitational force effect is to slow that planet down. And so it goes fastest here, slower, 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 and then it's going most slowly here, and then it begins picking up speed, and it's going fastest here. This is always remarkable for when I think about this, but Kepler came up with the rule that during equal amounts of time, the planets sweep out equal area. That's kind of remarkable. I mean, he had all this geometry written out, and when he looked at his data for the orbit of Mars and other planets, what he found was that they were sweeping out equal areas in equal amounts of time. And so he was able to develop that, not using calculus. Calculus had not been developed, but by using approximation techniques for determining the areas through different portions of the ellipse. Okay, and then the third feature that Kepler came up with was that the square of the planet's orbital period was proportional to the cube of its mean distance. And for that, you could use the semi-major axis. That's the same thing we found out. Now, we derived that only for circular orbits. Let's see if we can find that. So, this stuff. The stuff we had derived, this expression in particular, says that the period squared is proportional to the distance of the orbit, the radius of the circular orbit. Now, what Kepler had found was something more general. He found that if you took the semi-major axis, so he's working from this. So since there is no r, this is not a circular orbit, Kepler found that it was proportional to s cubed. So let's take a look and see. Here is some planetary data. And So we can take the mean distance. This is actually in terms of the mean distance. So if you pick any one of those distances for the orbit, you could use the major axis, you could use the minor axis. All you need is something that's proportional here. And so it works if we take the mean distance, here it is, and then here is the period in Earth years. So this is the distance from the sun and the period in Earth years, and when you put those values in, it turns out that that's the number you get for all the planets. So taking s cubed and dividing by t squared gives you the very same number for all the planets. So this is, data that's accurate to 3 significant figures. You can see a little variation back and forth. If this were carried out more carefully, you would see the numbers line right up beyond that. So yeah, this is something that Kepler had come up with during that time. So here it is. Here is the expression. Kepler's laws, we now understand, can be derived from Newton's laws for gravity. So the same thing we did with the circular orbits, Kepler did in general for any type of elliptical or circular orbit, and was able to come up with this formula. So if the period's here, if this represents 2 objects orbiting a central object with lots of mass, then that ratio of their periods squared will equal the cube of their distances squared of the orbits. So that has to be measured from this. If we have 2 satellites in orbit, so let's say we go back and we look at that satellite in geosynchronous orbit versus the satellite in low orbit. If we take the ratio of the period squared, that will be equal to the cube of the radius of the orbit for each one. So we can do ratios in order to come up with these calculations. All right, here's an example. It says, where is Mars? Mars period, noted by Kepler to be 687 Earth days. So that's 1.88 Earth years. So that's the value for Mars for the period. Determine the distance, the mean distance between the center of the Earth out to where Mars is located. What's the mean distance of Mars orbit? And here we are. So here's the sun, here's Earth orbiting, here's Mars orbiting, and what we're saying is that the period of Earth, we'll call that 365 days, it's actually 365.25 days. Mars is 687 days. The ratio of the periods here is 1.88, and so we can put that into here. And then what we can do is we can solve for the ratio of the radiuses of the orbits. So the ratio of the radiuses of the orbital motion for Earth and for Mars is going to be given by T2 over T1 to the 2/3. So we'll take the cube root of each side, and that's going to give us a 2/3 power. It says that if the periods are in a ratio of 1.88 to 1, then the radius should be in a ratio of 1.52 to 1. And putting in, Earth's orbit, the mean distance for Earth's orbit is called 1 AU. The mean distance for Mars orbit then would be 1.5. Again, all these are measured from the center of the sun. That would be 1.52 astronomical units. So we use these units, astronomical units, kind of a funny name, to designate the radius of the Earth's orbit. So 1 AU, the Earth's orbit, is 150 million kilometers. That tells us that Mars at 1.52 AU is going to be 228 million kilometers. So yeah, we can use this ratio approach, which can be derived using Newton's equations, which we did for circular orbits, or we can treat it as one of Kepler's laws of motion, which works. The two approaches agree with each other. Okay, now this is an interesting idea. What we could do then, we could find out how much mass the sun has. Determine the mass of the sun by doing this. Let's see what things we have to know. If we have something in orbit, something that's a relatively lower mass object, in orbit around something with a much higher mass, then we can treat the higher mass object as if it's at rest. So this works for the Earth and the Sun. The Sun has is 330,000 times more mass than the Earth is, something like that. And so we can treat the Sun as not moving, treat the Sun as if it's fixed, and treat the Earth as being in orbit around the Sun. And then what we can do is we can take this, let's see where we've got the numbers here. I guess I didn't write down the R. I need to go back to the slide before, just to remind ourselves. We're going to take this number. We're going to take the value of the distance between the center of the Sun out to Earth's orbit, on average, is 1.50 10 to the 11 meters, also known as 150 million kilometers, also known as 93 million miles. So we're going to use the formula we've derived. Well, we derived this for circular orbits, but now that we know that for R, it doesn't have to be perfectly circular. We can put in a mean distance instead, an average distance. And so we'll use that value that we saw on the first page before. Here is 1 year. Here is 1 day. So we're going to do some conversions. And here we go. The mass of the Sun, then, we can take this equation and solve for m. Now, in that equation, the mass of the central object remains. The big M is whatever the mass of the central object is. The mass of the orbiting object has canceled out. So that's kind of interesting too. Using this technique, by measuring orbital period, we can find out the mass of the central object, but we can't find out the mass of the object that's orbiting. As long as the object is relatively small in mass compared with the central object, it can have the same orbital properties. It can be placed in the very same orbit. So, if Earth were twice the mass, or 4 times the mass, or 1/10 the mass, it could be in this very same orbit. The very same orbit would still work. So we can take this equation and solve for the mass of the central object, which is the Sun, and then we put the numbers in. So if we have measured the gravitational force constant, we talked about how that would be done in a laboratory, and we do that in Physics 4C as one of our labs here. So we can get a measurement of big G. This is the number of seconds in a year. So, a year is like 31 million, 32 million seconds. That's why they fly by so fast. You go, wow, another 32 million seconds went by. So that's a year for the period of the orbit. And then the distance here, 150 million or billion meters. That's back to standard units. So this is now in meters. That gets cubed, this gets squared. All the units cancel out, except for one factor of kilograms. So I've got a kilogram squared here, there's a kilograms here, one of those cancels. I have kilograms in the denominator of a denominator. That will get brought to the top. Check it out, this is also a good problem. We looked at one similar to this earlier. Good problem for checking units. We're going to end up with units of kilograms. And the number that this came out to is 2.0 10 to the 30th kilograms. So this method works. In fact, that's how we determine masses of the sun, is by looking at the orbital properties taking place here. So a couple of things that have developed due to these planetary formulas. All right, these are not these are not to scale. Here's the Sun, Mercury, Venus, Earth, Mars, Jupiter. So here's a bunch of planets in the solar system, and boy, they didn't even get the distances. The distances are okay, but certainly not the sizes of the different objects. The diameter of the Sun is more than 100 times the diameter of the Earth. So if the Sun were this big, the Earth would be really, really tiny. You know, one example I like to use is if the Sun were at the size of a tennis ball. So here's a tennis ball, let's use that as the Sun. The Earth, on that scale, would be a tiny, tiny little speck, less than a millimeter, and it would be all the way across this room. So, you know, like 10 meters away, 8-10 meters away. So here's the Sun, size of a tennis ball. Earth is a little tiny speck, and it's located far, far away. And then the next closest stars would be the nearest star would be about 1,000 kilometers away. So the nearest star next to the Sun would be like in Denver, right, or Seattle or something like that. All right. Anyway. These are some examples of, well, they're the planetary system in our solar system, but astronomers now have discovered other planetary systems, as you probably know, maybe not, that astronomers have begun to assemble lists of planets orbiting other stars. And in some cases, some of these lists of planets, there are several. So, you know, here's Ursa Major, which is, I guess it's a star in the Big Dipper. And we've identified a planet around that star, and it's 3 times the mass of Jupiter. And then here are some around a star in the constellation Andromeda. And again, we've got 3 planets here that are relatively large kind of planets. And those are the easiest ones to pick up. So many of the planets that we've identified are they're big planets, you know, as big as Jupiter or bigger, and they're orbiting closer to the stars, and that's how we're able to observe the wobble. The stars actually wobble back and forth a little bit as the planet orbits. Planets that are that much mass and they're very close to the star create more of a wobble, and that can be observed. So interesting, we really have discovered planets orbiting other stars. Many, we have hundreds of these listed now. Here's kind of an interesting example. There are these places in space where we can place an object. We can place a satellite, for example, and those points in space will become stable points for the satellite to orbit the Sun. And so here's an example. Let's say that we place a satellite somewhere between the Earth and the Sun at some distance. And now we would expect if this object were just orbiting by itself, it would be going faster than the Earth, right? So it's going to feel a certain gravitational attraction to the Sun. It's going to need to be moving faster if it's in a stable orbit. But because of the presence of Earth nearby, this object doesn't, well, it feels the effect of the Sun, but it also feels a gravitational attraction back towards Earth. So what this is showing is that when you look carefully at the regions around the planets, objects orbiting could be affected by the presence of a planet. The asteroid belt in our solar system is certainly affected by the presence of Jupiter. Jupiter's presence has an effect on the orbital properties of the asteroids. So this is Earth, and there's this location where we can, they're called Lagrange points. These were identified by mathematician Joseph Lagrange. There are 5 different locations that Lagrange identified. Now, what we're trying to do here is find out where just one of those would be. This is kind of the easiest one. And these are a bit of a challenge to go in and determine these Lagrange points. So here is the satellite. It's going to be a force of gravity towards the sun and a force of gravity towards the Earth. And that effectively is going to reduce the force of gravity acting on that satellite from what it would be if the Earth were not present. That means it doesn't have to orbit quite as fast. So it's in an orbit a little closer to the sun, but it doesn't have to orbit quite as fast. There's going to be some point between the Earth and the sun where those effects exactly balance in a way where the satellite will just keep up with the Earth. It'll end up with the same orbital period, so we can keep the satellite at that location. It's not orbiting the Earth, it's orbiting the sun. Okay? And the Earth is helping to have an effect. So the first thing we should point out is we're going to assume for this problem that this distance from Earth should be pretty small compared with the distance between the sun and the Earth. We're going to call this distance d. That means that the radius of this orbit for that satellite, or it could be a space station, right? We build a space station, we build it at a Lagrange point, and it's just a stable location with that orbit. So here is our acceleration and force diagram. Here is the satellite. It's being pulled towards the sun, it's being pulled towards the Earth. There's an acceleration taking place. We're assuming the force from the sun is going to be larger. It needs to be larger if we're orbiting the sun. And then here are the expressions. So the force acting towards the sun would be big G, mass of the sun, mass of the satellite, divided by the radius of that orbit. And the radius of that orbit is going to be r, the radius of the Earth's orbit, minus d squared. And then the force coming from the Earth, big G, mass of the Earth, mass of the satellite, divided by d squared. So the mass of the Earth is different from the mass of the sun, the distances are different, those have to go into the formula that we have here. And so that's going to give us a net force, and let's do some kinematics here. So this is the orbital period that we want. We want that satellite to have the same orbital period as the Earth. So we're going to write down the Earth's orbital period in terms of the orbital formula that we developed. So the Earth's period is given by this expression. Now, for the satellite, the acceleration that we're looking for then would be 4 pi squared radius of its orbit divided by period. But for the period, we're going to use the Earth's period. So we're going to take this expression and substitute it into this formula. Now when we do that, some things cancel. The 4 pi squareds cancel the 4 pi squareds. And for that satellite at the Lagrange point 1 that we've identified, it's going to need to have an acceleration of big G, mass of the sun, mass of the sun, times r minus d over r cubed. So that minus d is going to change our numbers a bit here. So here's what the setup looks like in terms of these forces. So I'm writing down from the previous page, force of the sun minus force of the Earth in terms of the direction of the acceleration. So I've written those down. There's a bunch of algebra taking place here. So here is the acceleration expression that we derived on the previous page. That needs to be the acceleration of our satellite. These are the forces acting on it. And at this point, the mass of the satellite has dropped off. right? If we go back, let's see what we had here. Notice that the acceleration was in terms of the mass of the sun, r minus d over r cubed. These were the two forces. And so what we've done on the next page is we've taken those two forces and divided through by m the mass of the satellite. This is a motional equation looking at the satellite's motion. So the m's cancel out. What we were talking about is, hey, we don't need, the mass of the orbiting object drops out of these equations. The mass of the central object stays in the equations. Okay, so the mass of the orbiting object has dropped out. This is the acceleration is equal to the sum of the forces divided by mass. Now, what I did was I made a definition. I said that x is equal to d over r. X is whatever portion of d of r that d is. And so d can be replaced now with x times r. Everywhere I've got an r minus d, I can replace that with 1 minus r times 1 minus x. Substituting that in, that allowed me to cancel a lot of stuff. The big G's all canceled. So it says that this setup doesn't depend specifically on the value of the gravitational constant. But now I got a bunch of 1 minus x's here, I got a 1 minus x squared here, and I got an x squared here. So I was able to cancel out all the g's, all the r's, and I'm left with an equation just in terms of x, that variable that we defined, that ratio of distances. And I've got the mass of the sun, the mass of the earth, and it's a fairly complicated expression in terms of x, but it is just in terms of x. So what I did was I multiplied through, and then I have, to get rid of the denominators, and then what I ended up doing was canceling out. We have an x squared expression here, and we have an x squared here. We're going to end up with an x squared when we multiply this out. So what I've done, make sure we get this straight. What I've done is I brought the mass of the earth term over to here, and brought everything that's the mass of the sun and brought it over to the other side. So this was getting rid of the denominators, and then this was combining everything for mass of the earth and mass of the sun. And so I ended up with this equation. Now at this point, we're assuming x is much smaller than 1. So this distance is pretty small. So multiplying everything out here, I ended up with, the x's on this side dropped out. So the x's were small enough I could ignore them. And that leaves me with a 1. On the other side, I'm keeping the 3x, but I can ignore the 3x squared and the x cubed because they're smaller. So these are kind of the same arguments you've heard in your calculus classes when you're taking derivatives or defining what a derivative means. And so we're going to ignore these smaller terms and just keep the 3x. And then it says approximately the value of x would be given by this expression. It's given by, in terms of the mass of the earth, the mass of the sun, and so 3x cubed equals that ratio. So this is way involved. This is an interesting example to look through to see how these calculations are done. I wouldn't put anything like this on a midterm, for example. So carrying through with this and simplifying to get a value of x, then we put in the masses of the earth and the sun, and the value of x worked out to be 0.010, which is about 1/100th. So it works out that very, very similarly to 3 sig, I should have put one more 0 here. It worked out to 3 sig figs that this is like 1/100th. Now, putting in the values of Earth's orbital radius, 150 million kilometers, that says the satellite would be about 1% of the way towards the sun. It would be at 1.50 million kilometers. So just to compare that with the moon distance, that's much farther than the moon. So it would be four times as far away as the moon. So at a distance about 4 times as far away as the moon, but it has to be lined up with the direction of the sun. There is this Lagrange point. If we place a satellite there or place a space station, it could be in an orbit that would keep it at that same relative location, relative to the Earth as it orbits. Now over on this side, I took the exact expression and then I programmed this in my calculator just to compare, to see how well this approximation worked. So I plugged these numbers into my calculator and I ended up with x is equal to 0.009967 or 1 over 100.34. So the approximation worked really well, ignoring those bigger terms in x. So basically what we did was we kept the leading term, which would be 3x cubed. On top we ignored those. On the denominator we ignored these. That leaves us with 3x squared. That was the approximation, and the approximation came out really close to the more exact number, programming this into a calculator. So just for comparison there. All right, here they're talking. Let's move on a bit. We looked at orbits. One example with orbits and measuring mass that's maybe interesting is the first measurements of Jupiter's mass were done in the 1670s, I believe. It dates back 350 years. As soon as Newton had developed these formulas, it was possible to go in and follow the orbital periods of Jupiter's moons. So Jupiter's moons, you could measure the orbital period, you could follow them in a telescope and see how long they took to orbit around Jupiter. And then you could estimate their distances, again, using the telescope and estimating how much distance within a telescope. You could use those numbers to determine the mass of Jupiter. Now you couldn't do that with Venus, for example, because Venus has no moons. There was nothing orbiting Venus, so that was not a calculation you could carry out. But for planets with moons, where you could follow the orbital periods, you could determine what their masses were. All right, let's move on. Now, they're introducing this idea of gravitational field, but we've been talking about it now since chapter 2, I think, when we first introduced little g. So I am going to say that we're already kind of familiar with this. Just a comparison with what are the fundamental forces in nature. There's a gravitational force, so this is the first fundamental force in nature that we have discussed. Now there's an electric-magnetic force, often referred to as electromagnetic force. Electromagnets are also devices we build, so that it can be kind of confusing. In any case, you can think of the electromagnetic force as having different components to it. There are electric components to that force, and there are magnetic components to the electromagnetic force. And there's a couple of what are called weak and strong forces, which certainly show up within the nucleus, but they show up in other types of particle physics also. So we will spend a good portion of Physics 4B introducing electric and magnetic forces and talking about those properties. Physics 4C, we will be looking at towards the end of Physics 4C, we'll be looking at the weak and strong nuclear forces. The strong nuclear force holds quarks together to form protons and neutrons, and then holds the protons and neutrons together within a nucleus. Weak nuclear forces enable particles to what we call change flavor. It's responsible for certain types of radioactive decay.
And we'll take a look at that in Physics 4C. So those are the fundamental forces. Now, anything else we talk about is going to be something related to one of these fundamental forces. So when we talk about normal force, we talk about normal force, objects coming up and running into each other, bumping into each other. Those are electric and magnetic forces between the atoms and molecules on one side and the atoms and molecules on the other surface that we have. So when we think about also the forces holding atoms and molecules together, the forces holding atoms and molecules together, holding the electrons together with the nuclei, those are electric and magnetic forces. At larger scale, planets, stars, galaxies, what's holding those together, what's holding everything in orbit, and that's gravity. So everyday forces that we experience, pushing against the wall, sitting on something, things bumping into each other, those are electric and magnetic effects between the atoms and molecules. The large-scale forces are gravity. And the reason for that is gravity is cumulative, right? If you got more mass, you got more gravity. What happens with electric and magnetic forces is because you've got electrons and protons in nature, the positive and negative charges, once the electrons combine with protons, then the forces tend to cancel out. So atoms and molecules form, but once those are formed, the leftover attractive forces due to electric forces tend to be rather small, okay? So, or not as significant. So again, these are kind of these are the fundamental forces of nature. Now, black holes, what are black holes? And that's a situation where we have enough mass concentrated into a small enough region that the gravitational fields become very, very extreme. Newton's classical description of gravity gets this wrong. So Newton's description of gravity does not predict the existence of what we now call black holes. They come from Einstein's general relativity. And so Einstein's general relativity, or Einstein's idea for general relativity, originally came from this. It came from what's called the equivalence principle. Einstein said, look, and this is something physicists had been wondering about for hundreds of years, there's an inertial mass of objects, there's a gravitational mass, and apparently they're the very same thing. So whatever inertial effects are created are identical to gravitational effects. So when something's accelerating, acceleration and gravity produce identical effects. So here's an example. Let's say that a person is standing on some bathroom scales. They're on the surface of a planet. They're inside a spacecraft, but they're sitting on a planet, and they're trying to determine, I forget, am I on the planet still, or did I launch and now I'm out in deep space drifting around? And so the person drops a ball and goes, yeah, the ball fell to the floor, I must still be on the planet. But then the person goes, well, wait a minute, there's another possibility. What if I'm in my spacecraft and my very quiet propulsion system is accelerating me through space? What would happen then? You go, well, if the spacecraft is accelerating at 9.80 meters per second and I let go of the ball, what will happen is the spacecraft will accelerate into the ball. It'll catch up and run into the ball. What does that look like from inside the spacecraft? Well, it looks like the ball dropped and hit the floor. So for a person in an accelerating reference system like this, they can't tell the difference between an accelerating reference system and a gravitational field. So Einstein raised that, elevated that to the level of a principle and called it the equivalence principle, and said any effect that happens due to an acceleration could be duplicated with the gravitational field, and vice versa. There would be no physical way that you could determine whether or not you were in an accelerated reference frame versus being in a gravitational field. The G's and A's produce identical effects. Here's another example of that. Here's the person out in space, drifting through space, and everything's kind of floating around in the spacecraft. That would be, drifting through empty space, is the same thing as Einstein said, being, and this is the way it really appears to work, it'd be the same thing as falling in a spacecraft, free falling. So it could be the astronaut this time, is wondering, am I out in space just drifting, or am I just about ready to crash into a planet and I'm just in free fall? Because I can't tell the difference, right? In this drifting through space, everything's just floating around, maintaining constant velocity in some direction. And in this case, there is an acceleration taking place, matching the gravitational field, and as a result, the effects of gravity are not noticeable. And Einstein called this the happiest thought of his life, that whenever you are in free fall, you get in an elevator and somebody cuts the cables, whenever you're in free fall, it's effectively the same thing as turning off gravity. And that was the starting place for the development of general relativity. So kind of an interesting example here. One of the predictions from that said, look, if an elevator were accelerating and we had light coming into the elevator, within the elevator itself, it would appear the path of the light is bent. And so Einstein used this to predict that gravity would have the same effect. Because an accelerating reference frame, within an accelerating reference frame, the path of a beam of light would be observed to be curved due to the acceleration. And so Einstein said you should be able to reproduce that in a gravitational field. That was one of the early predictions from general relativity. Astronomers went out and were able to measure this effect by looking at light coming in from stars. So they took photographs of the stars in a region of space just before, in advance of a solar eclipse. So they took a picture of that region of the sky, and then when the sun was blocked out by the presence of the moon, when the solar eclipse occurred, they could still use their telescopes to take pictures of the star field. And they found out that the apparent, the stars that were lined up here, light appeared to be coming from a different location. So I guess this is star number 3. Star number 3 is here, but now the light that reaches Earth is curving around the sun, and that creates a different apparent location. So you could see the stars shifted in the region of space where their light had passed near the sun. And that was a gravitational effect, and the amount of bending matched up well with Einstein's predictions. Another feature of general relativity is that space becomes distorted. And so when we look at an event horizon, so when we look at the region around a black hole, so here is a black hole is consisting of what we consider to be a singularity. So it's a lot of mass that has collapsed down to what we think of as being infinitely dense. The mass is all still there, but the gravitation has become so extreme that we know of nothing that can prevent a gravitational collapse. And so Einstein came up with the geometry surrounding a black hole, the mathematics that explains the geometry. And what happens in approaching a black hole is you've got a path leading you towards the black hole and then a possible path leading away, let's say in the radial direction. Once you reach a distance from the center of the black hole, referred to as the event horizon, there are no longer two paths. There's only one path. There are still two paths. Both paths lead inward. So at point B, one path leads inward, and one path no longer leads you out. One trajectory just hovers at the event horizon. Once you've passed the event horizon, both paths lead inwards. There are no paths leading back out of the black hole going forward in time. You'd have to go backwards in time to find a path that would lead you back outside the black hole, or back outside the event horizon or the Schwarzschild radius for that. Okay, I know we've gone over here, sorry about that. Wanted to fit these last topics in. Here's our summary of the chapter. So the last stuff, the black hole stuff and the general relativity, those are things so that you're, more complete in your understanding of how these things all work. Those are not, take a look at the homework and you can see where the emphasis will be for the chapter. So I'm going to wrap things up there. If you guys have any questions, stop by. If you want to talk about general relativity, if you want to look at singularities and event horizons, we can take a look at that. One more thing, let me, as long as I've got it here. One of the easier formulas from general relativity says that the R value, the effective radius of this event horizon region, is given by the formula 2 big G big M over c squared, where c is the speed of light. When we plug those numbers in for the sun, it says that in order for the sun to become a black hole, the mass would need to be within 3,000 meters. You'd have to take the entire mass of the sun and collapse it down within a radius of 3,000 meters for that to occur. For the Earth, given the Earth's mass, you would need to take the entire mass of the Earth and reduce it down to a radius of 8.9 millimeters. So if you could get the Earth down to a diameter, of about 2 centimeters, which is pretty small, then gravitation would take over. Gravitation would take care of the rest. And once you got all of the mass packed into that smaller region, then this event horizon would appear, or would be present, and you would have these black hole effects that we've talked about. Okay, just wanted to get those numbers in on the Schwarzschild radius. Any questions at all, stop by office hours and we can take a look at those.